We'll begin this chapter by talking about modeling with differential equations. Now, a differential equation is an equation that contains an unknown function and one or more of its derivatives. For example, dy dt equals 2 minus 3y is a differential equation. The unknown function y. Now, how do I know y is the function I'm talking about? And do I know what the independent variable is? If we look over at the derivative in our differential equation, that tells us that our dependent variable is y, and it depends on t. In other words, t is the independent variable. So my unknown function y of t is called a solution to the differential equation. Notice we don't have a formula for y. We don't know what it is. We just have some sort of formula for the rate of change of y. Anyway, this unknown function that's called a solution to the differential equation is a function that, when substituted into both sides of the equation, produces a true or valid equation. Differential equations are used to model a quantity that changes over time, especially if something is known about the rate of change, even though the quantity itself is unknown. And one of the goals when you're working with these types of equations is to find out what that unknown function, what that solution is. One common and important use of differential equations is to model changes to populations. So let's see how that would work. Let's say we have some population whose size is n of t, n at time t. We'll construct a fairly simple model where there's only two things that change the size of that population. There's births, individuals being added to the population, and deaths, taking individuals out of the population. And we're going to make a couple assumptions besides just that only births and deaths are changing the population. We're going to, for one thing, assume that each individual produces offspring, and each individual produces offspring at the same rate, which is a constant rate that we'll call beta. Then the total birth rate, in other words, the total rate of offspring production at time t is, before I tell you what it is, let me just explain when I say total rate of offspring production, that's the rate at which individuals are added to the population. So it's not the individual birth rate that I'm talking about here. Beta is the individual birth rate. What I'm talking about, what we're going to fill in this blank, is the rate at which individuals are added to the population. Well, if each individual produces beta births, then to get the total number of births, we would multiply that by the number of individuals in the population. Similarly, for deaths, we will assume that there is a constant death rate per capita, in other words, per individual, and that every individual has the same death rate. Then the total death rate, in other words, the total rate of loss of individuals from the population at time t, is, again, the product of that death rate times the population size, the number of individuals in the population. That's pretty abstract, and having Greek letters in there doesn't help. So let's see a specific example of this and how the numbers would work. Suppose in a population of yeast, each yeast cell produces one new yeast cell every 2 hours. That would mean then that each individual produces offspring at a rate of 1/2 an offspring per hour. Now, I know that sounds silly because you can't produce half of a cell or half of a baby or whatever your offspring are. But this is a way of describing what the rate is. So think about it. If each individual could produce half an offspring every hour, then that would mean that in 2 hours you'd have a half plus a half of an offspring, which is one new yeast cell in this case. And that's what we said we have here, one new yeast cell every 2 hours. So that beta I was talking about in this case would be 1/2. Now let's suppose that at time t equals 7, and by this I mean 7 hours, I probably should have typed that. Suppose at that time there happened to be 10,000 yeast cells in the population. How many individuals are going to be born at that time then? Well, there's half of an offspring for each individual, and there's 10,000 individuals in the population. That must mean that at that time the population is producing 5,000 offspring per hour. Notice that what we did there was we went 1/2 times 10,000 equals 5,000. In other words, we used that idea of multiplying the individual rate times the population size. Now suppose each individual yeast cell lives for 100 hours and then dies. Then the per capita death rate is 1/100th deaths per hour. And again, that seems silly. How can you have 1/100th of a person or a cell die? You can't. A cell is either alive or not. But if we quantify it this way, you can think of each hour that individual yeast cell has used up 1/100th of its life. So you could think of it as being 1/100th of it has died. Anyway, in this case, our mu would be 1/100. Now let's again suppose that the population size at 7 hours is 10,000. Then the total death rate for the population at time t equals 7 is, well, you have 1/100th of an individual dying every hour, and there's 10,000 individuals, so we have 1/100th times 10,000, which would be, what would that be? That would be 100 deaths per hour. And again, what we calculated here was mu times the number of individuals. So let's add to our model the population size, which we don't know. Remember, we don't have a formula for that. I'm just giving it the name n of t, is being added to by births at a rate of beta times n of t births per unit of time. And it's being subtracted from by deaths at a rate of mu times n of t. And that would be deaths per whatever the time unit in the problem is. In other words, the rate of change of the population size is, well, it's going to be births minus deaths. This doesn't tell us anything about the actual size of the population, only how fast it's changing. Now, we can make this equation simpler by combining the individual birth rate and the individual death rate into a single constant called the per capita growth rate. We define this constant that we're going to call R for rate as being beta minus mu. So the individual birth rate minus the individual death rate. And so now we have our rate of change of the population size, remember, was beta n of t minus mu of t. If I factor out that n of t, I'll have beta minus mu times n of t. And we just gave that beta minus mu, the birth minus death rates, the new name R. So to kind of finish up example 1, where we had beta was 0.5, I wrote that as 1/2 up there. And mu was 0.01, which I wrote as 1/100 up there. So R, the per capita growth rate, which we've defined to be beta minus mu, is 0.5 minus 0.01, which I think would be 0.49. So the rate of change of the population is going to be 0.49 times the size of the population. So that's a single number that takes both births and deaths into account.